Hello everyone, my name is Haichi Wang from Tianjin University. It is my great honor here to present our latest work, an empirical study of test case prioritization on the Linux kernel. And first, let's dive into the background. The Linux kernel is crucial as it serves as the interface between the hardware and software, and thus ensuring its quality assurance is paramount. However, given its high complexity, test execution for the Linux kernel is quite costly. Our preliminary study indicates that a single regression test cycle takes an average of 4.6 days. This is why test optimization techniques are necessary to accelerate the testing process, and which is the research area we focus on. To further quantify the overhead of regression testing tasks on the Linux kernel, we collected data over 3 months from 2 kernel CI platforms, encompassing about 10,000 CI jobs. Through quantitative analysis, we found that the Linux kernel undergoes updates very frequently, and CI jobs are also triggered frequently. We further analyzed the time distribution across different stages in the entire CI process, and data show that about 40% of the time is spent on the compilation tasks, and thus the test execution cost accounts for more than 60%. And this indicates that TCP techniques can be applied here to accelerate the test execution process. TCP works by reordering test cases so that those more likely to reveal faults are executed earlier, and this way problems can be exposed faster without having to run all test cases. In the field of application software, TCP has been shown to effectively reduce test execution time by more than 80%. However, there is currently a lack of research on TCP approaches in the field of system kernels. Therefore, we aim to investigate the performance of TCP techniques in the Linux kernel. We have designed 4 research questions which evaluate the performance of different TCP techniques in the kernel from the perspectives of effectiveness, stability, efficiency, and the flaky test, respectively. And first, let's introduce the coverage-based prioritization techniques. The goal of these techniques is to maximize the test case coverage. According to how coverage is collected, they can be divided into dynamic coverage and static coverage. Techniques based on dynamic coverage require collecting the coverage of each test case on historical versions to guide the prioritization of subsequent versions. And static coverage-based techniques determine coverage through the static function call analysis. And similarity-based TCP techniques work by defining a similarity metric and maximizing the similarity of already executed test cases to determine the order. These techniques can be mainly categorized into text similarity-based prioritization and the distribution similarity-based. The third category of TCP is information retrieval-based TCP technique. It leverages traditional information retrieval models, and it determines the execution order of test cases by retrieving the similarity between test cases and code modifications. In summary, we studied 3 categories of TCP techniques, and comprising a total of 17 techniques were evaluated. The data is mainly collected from the above-mentioned 2 CI platforms, and the test suites contain 2 widely used test suites, case self-test and LTP. And in total, we collect more than 500 commits, and each of which includes more than 30,000 execution records. We then perform the data preprocessing on the collected data. And first, we start with test path mapping, where we match test cases based on the test passes in the execution records. And then we do the deduplication. Since the Linux kernel compiled under different configurations is considered distinct instances, We duplicated the test records and merged execution tasks that share the same kernel configuration. And finally, we analyzed the different test results generated by the same test case. And by examining the execution passes, we removed the flaky tests. And eventually, we returned 51 kernel commits, and with each version containing an average of more than 1,600 execution records. We use APFD, average percentage of faults detected, a widely adopted evaluation metric in the field of TCP. For most techniques, we follow their implementation as described in the original paper. And specifically for dynamic coverage collection, we use the gcov tool, and for static coverage collection, we rely on the static function call graphs. And for the first RQ, which focuses on the effectiveness, we evaluated all 17 TCP techniques on our collected dataset, and that we performed the significance analysis using the ANOVA test and the Taki post-hoc test. And the experimental results are shown in the table. And from the table, we can see that similarity-based techniques generally outperform other categories, and among which text similarity-based techniques achieve the best performance. And among the coverage-based techniques, static coverage and dynamic coverage achieve similar effectiveness. However, since static coverage have lower overhead, it will have better performance in practice. And among different strategies, the additional strategy is generally better than others. Information retrieval-based techniques show almost no effectiveness in the Linux kernel scenario, and even perform worse than the random prioritization. For the second RQ, which focuses on the stability, we aim to understand whether the prioritization results from each iteration can stably guide the TCP tasks of subsequent versions. And to this end, we designed different simulation scenarios for different techniques. For IR and static coverage-based TCP techniques, we select the prioritization information from the K versions prior to the faulty version to get the TCP task of the current version. And for the dynamic coverage-based techniques, we use the prioritization information from the current faulty version to sort the subsequent unfaulty versions. And for the similarity-based techniques, since their prioritization depends on the test cases themselves, we use the evolution of the test suite to evaluate their stability. The graph shows the average data across multiple versions. In fact, most techniques show little change in stability. By comparison, text similarity-based technique and static coverage-based techniques exhibit relatively high stability. And for the third RQ, we evaluate the additional time overhead required by the different TCP techniques. And we consider the three stages in the TCP process: data preprocessing, prioritization, information collection, and sorting. And the results show that coverage-based techniques have significantly higher time overhead than other techniques. And for example, dynamic coverage techniques require more than 70 hours of additional overhead, and which is almost unacceptable in practice. And in contrast, the average overhead of the other two categories of techniques is within 1 minute. To verify the impact of flaky tests on TCP techniques, we conducted evaluations using data from which flaky tests had not been filtered out. And we found that most techniques are significantly affected, with the only exception being the dynamic coverage-based technique using the total strategy. And for similarity-based techniques, flaky tests have a very significant impact on them. And combining the previous conclusion, similarity-based techniques achieve better effectiveness with lower time overhead, but they are heavily affected by the flaky test, This also indicates that in industrial practice, more attention should be paid to identification and filtering of flaky test cases. In conclusion, this empirical study on test case prioritization for the Linux kernel makes several notable contributions. It is the first work to explore TCP effectiveness in the system kernel domain, and it investigates three categories of TCP techniques and evaluating them systematically from four perspectives: the performance, the stability, the efficiency, and the impact of flaky test cases. And among the techniques, similarity-based techniques, for example, using edit distance, generally achieve strong performance. However, they are sensitive to flaky test, highlighting the need for robust flaky test identification and filtering in industrial practice. For coverage-based techniques, static coverage approaches are more useful in practice due to their low overhead compared to the dynamic coverage techniques. And additionally, a system kernel regression test dataset and associated code have been organized and open sourced, facilitating further research in this area. And this is our recent work, an empirical study of test case prioritization on the Linux kernel. Thanks for listening.